Hi. I want to start today by saying thank you to Dave Jones. Dave gave me a shout out last week, and I do genuinely appreciate that. If you don't know Dave, he is a full-time YouTuber and electrical engineer based out of Sydney. Dave being a full-time YouTuber, I'm assuming that that's how he pays his bills. So if you haven't subscribed to him yet, what are you doing with your life? The goal today is to be able to add two numbers together. Before I get to that though, I punted in the last video the issue related to power, and in order to get two numbers to add together, I actually have to solve that problem. I'm not exactly sure how long this video is going to be, but I do expect it to be a long one. If it starts approaching an hour, I'll probably break it into two. We'll figure that out as we go along. Got a lot to get done, so let's get right into it.
Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey.
Okay, at the moment I'm running the test code that I wrote at the end of the last video. This is the code that works on conditional execution based on what's happening up here with the carry flag that you see coming on and off every once in a while. At the same time, I was able to get the voltage issues down here sorted, and it was nothing more significant really than replacing these board interconnects. I used virgin wire that hadn't been used before. I had been reusing wire for my power connections. Just simply rehooking that up seems to have made the difference. I'm running at about 4.9 volts right now, between 4.85 and 4.9 volts throughout the build. I know that I'm pretty close to the edge there, and so what I'm about to do may end up re-breaking this at this point in time. Now this is going to be similar to what I did in the last couple of videos. I do need to add two more control ROM boards, and so these are going to sit in here right underneath control ROM 8 and 9. So this is going to make this ridiculously large. I'm going to need to add additional breadboard space here for additional jump locations. So this is where I'm bringing all my wires in to make all the interconnects. And I also need to, in order to support that, extend my address lookup farther down as well. So I need to insert this here and wire that up as well. And that is a lot to accomplish, and I'm going to do that all off camera. So between now and when you see me here in a couple of seconds for you, I will get all of this taken care of. Plus I need to solder up two more of these EEPROM replacements so that I can have enough signals to drive my ALU A asserts and ALU B asserts. Let me get that done. I'll be back. Okay, and here we go. Two new control ROMs here, 10 and 11. Some extra breadboard space here for making all of my interconnects. And I will admit that I actually powered this on and checked to make sure that I didn't create any new power problems by adding this new circuitry. And it does take just a second for it to come out of reset, but it was much longer, and I did end up adding two more power connectors here. So voltage and ground, VCC and ground. I'll probably end up having to add a couple more as we go through this. There's quite a bit on this board, but not a lot of power interconnects back to the main power source. But what I want to focus on first is over here on this section of the build, and I'll end up sliding over and zooming down whatever I need to do here. But let me give you a little orientation. Here I've got ALU A and ALU B. Now ALU B is going to need to have the ability to invert the contents of the bus coming in, which I'm going to use for subtraction. But ALU A, I started off doing something that I honestly don't believe I'm going to need to continue to do here. And I was going to distribute the ALU A signal between several of the different components associated with the ALU, not just the adder. So the logic unit and the shift units were also going to be selected through this demultiplexer here. Well, in reality, I don't need this. This just adds another layer of complexity. All I really need to do is present ALU A to everything and select which piece gets output back out onto the main bus once the computation is completed. So I'm probably going to pull these three because I don't need these ICs anymore. This just becomes a landing spot for my ALU A signals here. ALU B I'm going to have to keep, and I will end up changing this so that it's really just an exclusive OR instead of a demultiplexer here. because again, I only have on or off. I'm either selecting the natural state of the ALU B contents or its inverted state. So I just need to add those over here. That'll be coming in a future video. I also need to take my ALU Adder result and hook that back up into the main bus. So I will get that wired up. And so first order of business is to kind of clean this up a little bit so I can simplify my signals over into this section. And then we'll talk about where those signals are going to come from over here. Let me start with some cleanup down here. Let me reposition the build. Okay, I'm going to get started with ALU A, and I'm going to go ahead and remove all of the ICs here and get that cleaned up first. Okay, this now gives me room to drop in my ALU A connections. And so I hook into ALU A right here. So let me get those routed up there. And I'm going to put these under the board here. Okay, that's going to give me ALU A. Now, I do need to clean these signals up even though I'm not going to use the subtract yet. 74 AC 86. These are 4 2-input exclusive OR gates. Okay, so why replace the demultiplexer with exclusive OR gates? Well, I've only got 2 possible signals, or signal shapes, if you will, that will lead into the ALU. One is going to be the uninverted ALUB, and the other would be the inverted ALUB signals. Now, I've got a line driver in there in order to uncondition or just pass on the uninverted ALUB input. And I'm going to end up adding some inverting line drivers for the inverted ALUB input. And I'm going to need a signal to switch back and forth between the two. Now, the default being the uninverted ALUB input, the other being the inverted ALU input. Now I can select back and forth between those two using a single bit, where when the bit is off, the default state would be to pass on the uninverted ALUB input, and then the on state would be to pass on the inverted ALUB input. And so to condition that and make it symmetrical so that both sets of line drivers are never asserting onto that at the exact same time, I can use an exclusive OR gate, one of them wired as a buffer, taking one side of that XOR gate low, and one of them wired as an inverter, taking one side of that XOR gate high. I feed the same signal into the other input of each of those 2 exclusive OR gates, and I've got a buffer inverter pair. I've got 2 exclusive OR gates available here. I also have 2 hookup wires here for ALUB. And finally here I've got my main bus output, which will get hooked up into this. So let me get that taken care of real quick as well. All right, quick power on here. Watch the reset. Turned off instantly. Brilliant. Let me just get a quick cleanup done down here. Okay, now I'm focused down here onto Control ROM 10, and I am going to play a little bit with Control ROM 11 today. For Control ROM 10, the first thing I want to look at is demultiplexing the things that can assert out onto ALU bus A. And to do that, I'm going to use 74HC138 ICs. So I'm going to drop one in here, and I'm going to put a pin diagram up in the upper corner there. Put a second one here, because I have 16 things that I'm going to want to be able to assert out onto that bus. It's going to take 4 bits of data from the control ROM, and I'll use the 4 most significant bits for ALU A. Now, what that's going to give me. With the 74HC138 and all the 138s in particular, they've got the enable pins such that you can get up to 24 bits. So I could add a third one in here. 24 bits of demultiplexing without actually adding any additional logic gates. And to get up to 32, which would be the full 5 bits of demultiplexing, you only need 1 inverter added. I'm going to use that feature in order to not add any logic to the 74HC138s, but still get 16 possible things that are going to be asserting out onto ALU A. Now, how am I going to do that? Well, there are two active low enable pins and one active high enable pin that is on each of these ICs. The select A, B, and C, or the low 3 bits of the multiplexed address, if you will, are going to be tied together. In my case, the upper bit, bit 4, is either going to be a 0 or a 1. Here will be the fourth bit, or most significant bit, will be tied to the active low signal. And on this IC, the most significant bit will be tied to the active high signal. That way, this is active when that most significant bit is 0, and this is active when the most significant bit is 1. And then whichever address is demultiplexed is what actually gets pulled low. Let me start by wiring this up. I'll go a little slow on this because it may confuse some people. And let me get this power and ground set up, and then I'll come back and we'll start looking at how all those signals get routed. So let's start with A, B, and C. A being the least significant bit, B being the middle bit, that's pin 2, and C being the most significant bit of the select, that's pin 3. These are going to be tied up here to bits 6, 5, and 4. The next 4, 3, 2, 1, and 0 are going to be tied over here in the future. Now, the most significant bit coming off of here, so this would be bit 7, I'm just going to tie that there now, is going to be tied to the first active low enable there. And then I'm going to take that same and move this over to the active high enable. The active high enable is on pin 6. That way, when that most significant bit here is low, this is enabled. When that most significant bit here is high, this is enabled. So I've got two more enables that I've got to deal with. I have a second active low signal here, and then an active high signal here. And then on this IC, I have two active low signals. And then the final thing that I need to do is I need to take this, and I'm just going to take this and tie this up here so that my 8 bits of demultiplexed active low signals are in a row up here. And then I can take one of these and just drop it in, and it will pick up all 8 signals there. I need to do the same thing over here. So this is the 8th bit, and that's going to just come up here and be tied up there. The last thing to do is to take bit 6, which goes to C, bit 5, which goes to B, and bit 4, which goes to A. And that is all of the signaling I need to demultiplex all the different things that I'm going to use for ALU A. Got a little bit of cleanup to do now, so I'm going to do that cleanup now. I'm going to duplicate this exact circuit down here. This will be handled in a future video, but while I'm here, I'm going to go ahead and drop in these ICs here and get this wired up exactly like this. And then I'm going to take the 4 least significant bits and duplicate that entire thing over here for ALU B on these ICs. It's going to look exactly the same, except I'm going to the lower 4 bits here. These lower 4 bits on this one are not going to be used. Let me get all of that wired up, and then we'll come back and hook this all up so that I can start driving some of these registers out onto the ALU. Here we go. Now, while I'm wiring this up, I made a comment at the start of this that you can drive 24 different signals using 3 74HC or 74LS 138 demultiplexers without adding any additional logic. And that's simply because of the arrangement of the enable pins. For 24 signals, you need 5 bits of information, and focusing on the 2 most significant bits, 0, 0 is very easily handled with the 2 active low signals. 0, 1 is easily handled with 1 active low, 1 active high. 1, 0 is easily handled with 1 active high, 1 active low. You just have to arrange how those 2 bits are hooked up to each other. Now for 32, 1, 1, those same 2 bits, you're going to have to pass one of those 2 through an inverter and then hook it up to an active low signal. Okay, I'm zoomed pretty far back out again, and I'm going to be bouncing kind of back and forth between the control logic and the ALU. What I want to do is I want to catalog and identify all the different signals here on the ALU that I'm going to need and where they're going to come from, here out of the control logic, so I can get everything hooked up and wired up here. For me to be able to control the ALU, I currently need, and this is just the adder, this isn't the full ALU, I currently need 4 signals that I can identify. I need the 2 carry select signals. I need the assert of the adder out onto the main bus. I need the inversion for ALU B, which is not going to be used just yet, but I'm going to pull the signal for it, the signal wire for it, back to the control logic. And so I've got a 4-wire ribbon cable here that has those 4 signals on it. What I'm going to do is I'm going to drop this, let's say right here for now, and I'm going to extend it up to this point. So this is going to be my landing point here on what is the ALU A. I don't believe I'm going to need anything more here. So I'm going to extend those 4 signals up to there. And then now I can replace each of these with whatever is going to be here. I also need assert of R1 and R2 out onto ALU A. I also need to be able to assert R1 and R2 and the fetch register out onto ALU B. Now I've got line drivers for ALU B here somewhere. One of these is. I'm not exactly sure which. I'll have to identify that. So I need to come from here to my ALU B here. So I'm going to need some ribbon cables for that. Okay, so of these 4 signals down here, the 2 carry selects come from control logic 9, and they are the 2 most significant bits up there. So that is these 2 bits, and I'm going to connect a wire here and bring that out and around, and I'm actually going to drop it right in this jump point here. I'm not actually going to hook it up here and then drag it down. And the reason for that is quite simply because there's only one place it'll ever go, and they're already in the right order. So then I just need to extend carry select here up to these 2 signals here. The next one is invert of ALU B. And I've got room in control ROM 7 for that. I've got 2 available bits at the bottom, and I could actually stick it right there. But I do not yet have a control ROM 7 built onto the board yet. I'm also not a fan of taking 2 bits and separating them unless I don't have a choice, because I may come across something that requires 2 bits. But control ROM 8, which I do have, has the least significant bit available. And so what I can do with control ROM 8 is extend the least significant bit there over to the least significant bit on this cable, this ribbon cable that leaves that board. That'll bring that signal down here, but I'm not going to use it. So in the meantime, I'm going to take that signal and I'm just going to tie it low, hard code it low, or hardwire it low for now, so that I am always selecting these 2 line drivers. Future video will change that. The last one will be the main bus assert of the result of the adder back out onto the main bus. And to do that, I have this one. Now, ALU Adder, I have to figure out which of those demultiplexers it's on. The adder assert out onto the main bus up here is going to be controlled by, so this is going to be demultiplexer 3, 0, 1, 2, and 3. It'll be the most significant bit on that. So I drop this in here, and I've got a challenge now because the output for bit 8 is here, which needs to be brought up to that position up there. The other end of this, wrapping around off the build, is going to come down here to this location right next to and in line with all the other main bus asserts. So ALU A, we just built out, which we can pick up here. I'm going to bring this around and extend it over to this spot. ALU B, we also just extended out, and I'm going to bring this over and drop this about here. I'll leave a little bit more room here for this. All right, the last task here is to connect the ALU bus B and the fetch register to ALU bus B down here. So this is the least significant byte and then the most significant byte. Try to keep the LEDs visible. All right, Let me get some cleanup done here, and I believe I've got another one here, and then extend my signals to the right locations over here, and then we'll worry about getting things connected down here. Okay, we'll start up here in the corner, where this is a relatively simple connection to make. Next will be this signal here, which is going to be used for ALU bus B to invert that signal. This is going to be used in a future video, but the call out here is that it's treated like an assert signal, so it needs to be available for the entire clock cycle. Next is going to be extending these signals up, and I'm going to cheat by looking at my things down here. These two least or most significant bits are going to come up here to select A and select B. Now running these up the outside here under all this mess may prove to be a bit of a challenge. Next up is my inversion. That's the next one over. That needs to come over to this position here. Okay, and finally then it's going to be up here. This is going to be my main bus assert for the adder. All right, let me reposition and zoom down here so we can hook everything up. Okay, I'm zoomed down into this section here of the build pretty tightly. This is where I'm going to focus most of my attention, at least for the next this next segment. I've got what I count as 8 signals. I'll stick those up over there that I need to cross connect in order to get all of this working. And I'm just going to take them one at a time here and try to get them addressed. Now, these are the 3 signals that go off to my registers. This is currently the program counter, R1, and R2. Now, R1 will need to assert out onto ALU A, and right now I've got that signal pulled deliberately high. So I need to replace that now with a signal that's coming off of my ALU A assert, and that's going to be not the least significant bit, but bit 1, because the least significant bit is do nothing. I also have an assert onto ALU B. It is also deliberately tied high, and that needs to come from effectively the same location, but over here on ALU B assert. R2 looks very similar. ALU A is pulled deliberately high, but it needs to come from here on ALU A assert. ALU B assert is again tied deliberately high, and I'm going to replace that with the assert signal coming off of ALU B. Next is the fetch assert out onto ALU B, and that is over here. It is also tied deliberately high, but it comes from this ribbon cable I haven't hooked up yet, and I neglected to make this one, so I'm going to go ahead and drop this in here. ALU B, bring it down here and set it right next to the other one. Okay, and then bit 13, so this is 15, most significant bit, 14, 13, needs to come over here. So if I'm able to get this working, I will clean this up. Okay, and there's ALU B assert for the fetch register. Carry select I already have wired up here, so I'm good there. And then the last one is the main bus assert for the adder. The ALU Adder is bit 14 here, so 15, 14, and that's going to tie here. That theoretically is all of the wiring I need in order to actually get the adder to work over here. So with that, let me now recenter the build. And I need to write some code in the control logic. I need to write some code in the assembler. Well, update the architecture in the assembler. And I need to write a test case. And I need to get that done. I'll come back and we'll start executing tests and see just how close we got. Be right back. Okay, I've run into a bit of a concern down here. My test code requires 9 bits of address space, and I only have 6 of them tied to the address bus 1 input. The others are explicitly tied low so that I am pulling zeros for those addresses. I need to extend this all the way across to all 15 bits. Now there's 16 coming in, but only 15 bits addressable here. So I'm going to use the 15 bits there for that. Bit 16 will be used for the actual memory coming up shortly. So let me take a few minutes and reorganize this so I'm pulling all 15 bits properly, and then we'll start executing tests. So real quick to clarify here, the next step in the evolution of my memory module is going to use the most significant bit to slide back and forth between ROM and RAM. All right, I have reprogrammed all the EEPROM on the boards here. I do not yet have power hooked up, but I have been able to come up with 24 tests that I think I need to execute in order to confirm the functionality of what I've got going on over here. Most of my attention is going to be focused over here, maybe a little bit down here, and I will stick the code for each test up in the top. The first test is going to confirm, really overall, whether or not I can add two numbers over here. The rest of it is going to be just specific tests related to each of the different scenarios I can come up with. So let me pull up the tests on my end, and let's get power hooked up. Okay, place your bets now. Well, I did get a good reset. I have nothing resetting the results here. And test number 1 starts with a set carry. That'll go up there. Carry is currently not set. That executes properly. Then I've got a move of A into R1, and I did label these. And that worked. Forced a no op up. Now I've got a move of 5 into R2, which that worked. And now I should be adding R1 to R2, which should give me FFFF and storing the result back in R1. Sorry, that's that instruction. And that did not work. Now the problem is I don't know if it made it here to ALU A or not. Let's reset to find out. So that's asserting onto ALU A, that's asserting onto ALU B. I have different values in my adder, which it should be adding up to FFFF. So let's dig out the logic probe. All right, so R1 should be asserting out onto ALU A, and that's AA. So up here I should have high, low, high. All right, so the last 4 bits are high, and I'm not believing this should be. That should be, let's see here, ALU A. Okay, that tells me that I may still have a problem on this register asserting out onto ALU A. That I was not prepared for. So ALU B assert on this register is not working. Again, I was not prepared for that, although I probably should have been because I never tested it. All right, let's grab a schematic. I believe my problem is going to be on one of these line drivers where I need to grab my soldering iron and clean those up. Let's do some tracing backwards here. Okay, let's start with ALU A. And in the schematic here is ALU A output. And the line drivers are being fed by the output from the register. Now I know the LEDs are also being fed by that same output through, of course, their own line drivers. And the main bus is also being fed by the output of the registers, again, through its own line drivers. So ALU A, anything that's on that bus that is connected, if there was a short, it would be on the output side of the line driver, which means it could be on anything that's connected to ALU A. Right now, ALU A are just the register PCBs plus the bus backplane associated with it. So let's take a look at that. Okay, so this is the corner of the PCB in question. And if I zoom in down here on the bottom corner, this is ALU A bit 0, which is coming down here to bit 0 ALU A on the PCB. I believe that there's going to be two possibilities on why this is behaving the way it is. Either the first is I've got bridges here between adjacent pins, and I'm on continuity mode here. Slide that up just a little bit so you can see it better. And no matter where I test, if it's on any one of those boards, if there was a bridge, it would show up anywhere on that bus. And for the lowest 4 bits, that's good. So I don't believe I've got a bridge connection causing that problem. Option 2 is that I might have a floating input down here. So that's asserting out onto ALU A. So this first pin closest to me is actual ground. Next one up is bit 0, and that's floating. High, floating, and that pin actually looks like it's moving, and that's high, low. Okay, so I need to get this PCB out and get it under the microscope. Let me get that done. Okay, well, I neglected to hit the record button as I started soldering, and not only was that pin and that pin floating, but the ground pin was also floating, and so I managed to get all of those soldered back down. All right, so let me get the build back out. I'll throw it in there and give it a test again. All right, R1 is replaced. Let's give this a shot again. By the way, the flags aren't being reset properly, so I am going to have to look at that as well. Okay, so that latched fine. That latched fine. And now that I'm asserting, now I need to look to see what I am asserting off of R2. That should be high, and it's low. Low, high. So that's correct. This one's incorrect. It tells me that that pin is low. And that's floating there. Okay, I have to pull this one out, and interesting. I tap on it, and it changes, and that's because I've actually literally have a floating pin here. Okay, let me pull this. I went ahead and dressed up these solder connections down here. Let's give this a test again. Again, set carry, alternating pattern in R1, alternating pattern in R2. This is my add instruction, and now both of these are asserting out onto the ALU, and so my result is all 1s, but yet I'm latching 0s. So the question is, am I asserting? So that's high. Let's see if we can get it this way. High, 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 low. Then I am not asserting that. So my ALU adder is not being asserted out onto the bus. That should be this signal there, and it is not. Let's go check the code. Yeah. I'm not seeing anything assert out onto the bus, onto the main bus. All right, I'm gonna have to get that corrected. Let me do that. Okay, I made a quick change to control ROM 1. Let's give that a shot again. Here's my add instruction. Everything is set on, so that's good. And I got all kinds of a mess over here. So what the heck happened there? That's outputting correct. I've got the right value on the main bus. Now I am going to have to go get that crappy oscilloscope, because my suspicion is the value is disappearing off of this bus faster than this can latch it. Everything else appears to be accurate. Actually, load it. And that's that spiked clock signal. So that would be accurate, that it disappears too quickly. So I may have to latch the output here. Something I was not, well, I was mildly considering for other reasons, but my latency here, well, my latency in these counters to load, because of the spike clock that's up here off the top of the screen, is allowing this to disappear before this gets an opportunity to latch it, well, load it into the counters. Let me think. Okay, let me show you what I've got here. I've got my yellow trace hooked up to my load signal for R1. I've got my blue trace hooked up to the least significant bit of ALU A. Now I'll reset here and start stepping through this. I've got this in single shot, so I'm going to end up with 1 as I do the load for R1. And so now if I run, here's what I see. I see during this load signal, which is translated into a low on the actual register itself, the value is actually changing during that period of time. And I don't want that to take place. So, how do I solve for this? Well, I considered latching the output so that it was inconsequential if it did change, but I believe the better answer is to latch the input, because what that's going to give me is the ability to save the last thing that actually came into the ALU and display the results of the last thing that actually came into the ALU. And then that just gives me one additional latch signal that I need. I've got each of the flags have their own latch, and I just have an inputs latch, an ALU A and an ALU B, both having their a shared input latch. It's one additional signal to wire up. It's 4 additional latches I've got to put in place, but I think I can get that taken care of, and I believe that's going to solve this problem. So let me work on getting that done. Okay, let me try to knock this out quick. Okay, this signal here is going to tie back over here to my control logic. This is where I'm going to pick up that signal once I get it programmed in over here. I'm going to take these orange connectors out, and then these outputs off the line driver will hook up here and provide my inputs into these latches. And I'm doing this just to get things wired up quickly, because I want to get back to testing. My next decision here is one of real estate. I have an extra bit here on control ROM 8, but I really want to AND my signal with the spike clock, which is this brown signal coming down the side here. I have a NAND gate here that's available, and I have no room to expand into another IC location. On the other hand, control ROM 9 does have that ability. It has the extra real estate out here. I do have a spare bit in control ROM 9. I will end up, similar here, have 2 NAND gates, but I've got some room out here on the edge to put an AND gate in there. And so I'm going to actually do that here. I'm going to drop in an AND gate here, extend my signal across, pull my spike clock all the way across, and then pick up the output of that and drag that down here to this signal that I just hooked up. And I'm going to do that all with temporary hookups, just so that I can prove that this is going to work right. I need to collect some components. Okay, I've got control ROM 9 reprogrammed. I've got all my hookups taken care of. Let's see how lucky we can get here. Yeah, I didn't mess that up. Didn't mess that up. That worked just like it was supposed to. This is not working the way I want it to. This should still have all of the results from the previous add. What it looks like it's doing is it's adding R1 to R2, and it's got it stored there. Let me continue here. Okay, test number 2, quickly here. Set the carry, move a pattern into R1, move a different pattern into R2. And that result is stored in R2. So it looks like I'm getting close here, except I'm not getting the right behavior out of this, which means that I'm not getting the right behavior out of these latches that I just put in. So there's something that needs to happen then with this latch signal to clean that up, which is this AND gate that I just put in. Let me do some digging on that. Okay, I pulled out my crappy oscilloscope here. Let's see here. The yellow trace is here. That is on my signal that performs the latch over here. The blue trace is here, and that is on the actual signal coming from the control ROM. So the blue trace will be the signal going high, and then the yellow trace will be the actual signal that's sent off to perform the latch. Now recall that the latch happens on the rising edge. Let's see what those look like. My yellow trace is the actual signal. So that would be this spike here, which is exactly what I had intended to set that up to be. Now, the latch happens on the rising edge of this yellow trace, and I'm going to assume it's somewhere around here, about where my baseline is. So let's say that it latches somewhere about here, and I'm getting some delay, I'm getting some incorrect results here after that latch takes place, and that's because this is latching potentially too early. So what I want to consider doing is taking this signal and inverting it. What that would do is that would actually put the latch on the rising edge after the dip, so it would be high, it would come low and go back high, and effectively creating this much of a delay in that signal, the width of that signal right about there. So what I'm talking about doing here is I've got a signal that looks like this right now. I want to change it to look like this. So instead of the latch happening at that point, the latch is then going to happen at this point, creating a slight delay. I think I need that delay in order to get the correct behavior over here. Now, originally, let me get this out of the way real quick. Originally, I dismissed the idea of using the NAND gate because that wasn't the shape of the signal I was looking for. But now looking at this, I believe that actually is the signal I'm looking for. So what I'm going to do is I'm going to take this and route it over to the NAND gate that's available over here, such that the output now is coming off the NAND gate. Now my signal is still coming from control ROM 9, and if this works the way I want it to, I will change this. But let's re-execute that test. And that worked perfectly. That still has the last result in it. So it's got a new pattern in it for test 2, a new pattern in it for test 2. Now I'm adding, and that's the result in R2. Now I need to reset this so that it actually properly clears that out, and I can keep track of that. I will update my test cases to do that. But this looks much better. This looks much closer to what I'm actually striving for here. And I believe I've got what I need. Let me do a couple of things here. I want to clean up the wiring here and clean up this kind of mess. I want to take this control signal off control 9 and move it back to control 8. Clean up some of this and clean up the extra wire here. I've got some wiring that needs to be done here. So I've got quite a bit of cleanup to do here, but then I want to come back and I want to run through the entire gamut of tests. And before I do that, I want to change the test cases as well, so that the test cases actually will clear out the results register here, or the results here in the ALU, so that the ALU starts at zeros, because every other test I have has some value in there, so I can force a 0 in there now. All right, let me get this taken care of. We'll come back, and I think I'm close. I'm going to press on. I know right now we're probably looking at about 40 minutes, 45 minutes into the video, and I'm going to press on. I want to see if I can actually get all the way through this in this video. I'll be right back. This is where I pay for those quick and dirty hookups. It's going to take me a few minutes to get this organized a little bit. That said, once I'm done, I believe I'm pretty close to having this working properly. The only exception is the flags, which I haven't paid any attention to at all, so I may have to spend some troubleshooting and debugging time looking at the flags in order to get those sorted as well. But I feel confident I can get this wrapped relatively quickly. Of course, when I say things like that, things go awry. Let's see what happens. Okay, the last of this down here, I'm going to wait until I have good tests all the way through. But I do want to replace this cable down here that's got 4 plus this 1 extra. And I want to replace it with this cable that's now 6. And my thinking is, I think I'm going to need to add another signal, but I'm not exactly sure what it is yet. But that gives me the room to do that. The last thing I want to take on here before I start testing again is I want to tie all of the inputs of ALU A and ALU B to ground with a pull down resistor. Now this is a 1000 ohm resistor and I've used those all over the place. But I'm growing increasingly concerned that I'm pulling too much amperage. And as a matter of fact, up here, I've replaced a few of them with 10K resistors. And I'll likely go back and do that for everything, replacing all of the resistors with 10Ks. As a matter of fact, I've got some of those on order. And when those come in, I will make those changes so that I have a little bit less current draw and not so strongly pulled to ground. So let me get these plugged in. Like I said, I'll use the 1Ks until I get the 10Ks. Okay, this does now renew some concerns about the voltage drop and whether or not my voltage supervisor is going to like that change. So let's give that a test. And that's what I was afraid of. All right, so what to do? So the concern here is that if I parallel anything with a 1K ohm resistor, the value of the effective resistance is less than whatever the lowest value resistor is in that parallel. So anything I try to parallel with a 1K is going to end up resulting in something less than 1K. That's going the wrong direction. I do have the only two other value resistors I have in any kind of quantity is a 2 meg ohm resistor, and I have loose 5 meg ohm resistors. Now I can parallel the 2 meg and the 5 meg and end up with something like 1.4 meg ohm, but I'm wondering if that's not too weakly pulled down now. I think what I'm going to try to do first is drop in, I've got some values up here. I'll drop in some 2 meg ohm resistors and see if that will work and pull my resulting no-op low. These are LS logic, yeah. So there will be pull-up resistors in there. So let me give that a shot first and see if I can get these 10Ks replaced with 2 megs. My goal is still to use the 10K ohm resistors when I get them. Now, I'm not supposed to use these right out of the tape like this, but for a quick test, I'm hoping Dave will forgive me. All right, let's give this a shot. Okay, that did go into reset. Okay, that looks like it's pulling it down effectively enough. Maybe I will use the 2 megs all the way through. Tell you what, let me get these pulled low properly with 2 megs and we'll give this a proper test. Okay, let's give that a try. It does still take a while to come out of reset, but it does come out of reset. Let me go ahead and replace these too. All right, that does not appear to have done any damage. I need to get the control ROMs reprogrammed. So let me get that going and we'll come back and we'll do some good tests. Okay, I've got everything reprogrammed again with my new test cases. I'm an idiot because I was not paying close attention to the LEDs over here. With the pull down resistors here and here, my expectation should have been that all of these LEDs were out. They're not. I did replace one of these 2 meg ohm resistors with a 10K, and it does pull the LED low, which is what it should do. The other piece of this here is that I tried a 100K ohm resistor, and it did not pull the signal low. So 10K is the holy grail, and so I will wait for those to come in and then go ahead and replace all of the pull downs with 10K ohm resistors. All right, that said, reset, and my flags are not being reset properly. Now I took a look at this because my angle of viewing is not nearly as good as yours. And if I was to get up here and look at it, obviously my head would be in the way. My clear for the carry is this signal here, this yellow connector up here. But for all the other flags, that signal is right here, and they are off by 1. And so I really need to move that over 1 and get that into the correct position. So let me do that. Okay, so now power off, power back on. My flag should remain in reset. So no flags are set. That's much closer to the behavior that I'm looking for. Okay, so what I did is I have added a new instruction to move 0, a pseudo register called RZ, and these are done with pull down resistors on the main bus. These are they. So here are those pull down resistors here. So when I clock, R1 should be pulled to 0, which it will be. R2 will be pulled to 0. And then I should add R1 to R2 and store the result back in R1. So that should have something that should result in an add, and it's not. What have I done wrong? I am expecting the result up here to be 0. So move 0, add the two together. This should be 0. So let's see here. ALU A is asserting, ALU B is asserting. So I should be getting... Alright, so my new latch signal is not behaving properly. I don't believe I've got anything in here. Yes, I do. That's the one that's pulling it low. Aha! Extra wire. Alright, let's reset that and try that again. That worked. Okay. Why did that do that? Okay, that worked. Okay, so from here, this deteriorates into a number of connection issues and timing problems. And the timing problems are going to take more than I was prepared to put into this video to solve, and it's already getting quite long anyway. At this point, I was planning on splitting it into 2 videos originally when I recorded my intro. And now that I've reached this point, I've probably got at least another 30 minutes, if not longer, in video to record and get ready. So I'm going to call it here, and I'm going to dedicate the next video to solving all the issues related to the ALU adder and getting all of the timing correct. There's still just enough unknown that I'm pretty sure I'm going to get a good length video out of that as well. But by the end of the next video, my plan is to be able to add 2 numbers together reliably. Also in the next video, I will have those 10,000 ohm resistors, so I'll replace all the pull downs and make those correct, so I'm not pulling so much current. We'll see you soon.